You know that feeling when you click on an app and it just appears instantly? That incredible speed, that's all thanks to something called RAM. It's your computer's short-term memory. But here's the weird part. It holds everything your computer's thinking about right now. But the second you cut the power, poof, it's all gone. So today we're going to get to the bottom of how RAM actually remembers and, well, why it's so incredibly forgetful.
And that really gets you thinking, right? How can a silent, flat piece of silicon remember anything? I mean, it's not like it has a brain. And what's the deal with it having total amnesia the moment you pull the plug? The answer, and it's pretty cool, involves billions of microscopic buckets and tiny, tiny electrical switches.
So here's how we're going to break it all down. First, we'll start with the big picture, what RAM's job really is. Then, we're going to zoom all the way in, like microscopically, to see how a single bit of data is stored. We'll look at the two main flavors of RAM, figure out how billions of these things get organized, solve that mystery of why it forgets, and then we'll take a little peek into the future.
All right, first up, let's get our heads around this with a really simple, but honestly a perfect analogy. You gotta think of your computer's RAM as its personal active workbench. Okay, so picture this. Your RAM is your desk. Your computer storage, that's your SSD or hard drive, that's the big filing cabinet in the corner. To get any work done, you go to the cabinet, pull out a file, and put it on your desk. The desk is for what you're doing right now. It's fast, it's right there. The filing cabinet is for long-term storage. Now, when you're done for the day and you turn off the lights or the power, you clear off your desk, right? But everything in the filing cabinet stays put. That's the key difference. RAM is all about speed, not about permanence.
All right, you ready? Let's go microscopic. We're about to zoom way, way down, past all the circuits, to look at the two little components that, when they work together, are literally the foundation of all modern computer memory. So meet the first hero of our story, the capacitor. Its job is incredibly simple. You can just think of it as a tiny, microscopic bucket. Seriously. But instead of holding water, it holds an electrical charge. And whether that bucket is full or empty, that's how a computer stores a 1 or a 0. And of course, every bucket needs a tap, right? That's the transistor. If the capacitor is the bucket, the transistor is the little gate or switch right in front of it. Its entire job is to just open and close, deciding if electricity can flow into or out of that bucket. That's it. So how do these two actually store a bit of information? Well, it's this really elegant three-step dance. First, the transistor switch opens up. That gives us access to the capacitor bucket. Second, we either fill the bucket with charge to represent a 1 or we make sure it's empty for a 0. And finally, the transistor switch slams shut, trapping that state inside. A full bucket is a 1, an empty bucket is a 0. Your RAM is just billions and billions of these little pairs working together.
Now that little transistor capacitor team we just saw, that's the basis for the RAM you probably have in your computer. But there are actually two main flavors of RAM, and knowing the difference is super important for understanding why computers are built the way they are.
Okay, so on the left, we've got DRAM, which stands for dynamic RAM. This is our simple one transistor, one capacitor combo. It's cheap to make, so we can pack a ton of it onto a memory stick for our main system memory. But on the right, you have SRAM, or static RAM. It uses this much more complex setup with like 6 transistors and no capacitor at all. This makes it insanely fast, but also way bigger and way more expensive. And this trade-off is everything. It's why we use huge amounts of the cheaper DRAM for our main memory and just a tiny little bit of the ultra-fast, expensive SRAM right next to the CPU as its cache.
And here's the catch with DRAM. This is why it has that D for dynamic. You see those tiny capacitor buckets? They leak. The charge that represents a 1 just trickles away in milliseconds. So to stop it from forgetting, the computer has to constantly run around and top off every single one of those billions of buckets, thousands of times a second. It's this constant, dynamic effort called a refresh cycle just to keep the memory from fading away. So let me get this straight. We have billions of these leaky buckets that all need to be refreshed constantly. How on earth does a computer keep track of all that? Well, luckily, it doesn't just throw them all in a big pile. They're actually laid out in a brilliantly simple and organized way. Just think of it like a massive city map. It's a perfect grid. Every single one of those little memory cells or buckets sits at an intersection. The horizontal streets are the rows, called word lines, and the vertical streets are the columns, called bit lines. This means every single bit of data has its own unique coordinate, like a street address on the map. And this grid system is exactly what random access means. It's not random like chaotic or unpredictable. It means the computer can jump directly to any address, any coordinate on that grid, instantly. It doesn't have to start at the beginning and read through a bunch of other stuff to find what it's looking for, kind of like an old cassette tape. That ability to go anywhere, anytime is what makes RAM so incredibly fast.
Okay, so we've seen how RAM uses these charged-up buckets on a grid to remember things. But that brings us right back to our original mystery: why does it forget everything the second the power goes off?
The secret is actually shockingly simple. RAM's memory isn't a physical thing, like ink on paper. It is literally nothing more than the temporary presence or absence of electricity in those billions of little buckets. The ones and zeros are just patterns of charge. So when you turn off the power, you've pulled the plug on the very thing that makes the data exist. No power means no charge, and no charge means no memory. It all just goes back to neutral.
I absolutely love this quote. It just captures the idea so perfectly. RAM is like a chalkboard written in lightning. It's incredibly clear, it's super bright and fast, but it's gone the very instant that energy fades away. It's designed to be temporary.
But what if it didn't have to be that way? What if we could have the best of both worlds? For our last section, let's look ahead at some new technologies that are trying to give us the speed of RAM, but with the permanence of a hard drive.
The future is all about something called non-volatile RAM. Instead of relying on a leaky electrical charge, these new types of memory use physical properties that are way more durable. You've got MRAM, which uses tiny magnetic fields, kind of like microscopic compass needles, pointing north or south for a 1 or a 0. Others use changes in a material's resistance. But the goal for all of them is the same: to store a bit in a way that doesn't just disappear when you cut the power.
And think about what that would mean. The implication is huge. We're talking about instant-on computers. Imagine never ever having to wait for your computer to boot up or for an application to load. You just turn it on and bam, your entire digital desk, your workspace, is exactly how you left it, instantly.
So we've seen that today's RAM is basically lightning in a bottle. It's brilliant, but it's fleeting. The future, though, might give us something more like a diamond, just as fast, but totally permanent. So I'll leave you with this. What would it mean if your computer never had to boot up again, and every single thought was saved the very instant you had it? It's a pretty wild idea that could completely change how we use technology. Thanks for joining me for this one.